Привет! Данный курс скачан с сайта SuperSliv.biz. На сайт ежедневно добавляются топовые материалы от крутых авторов и лучших онлайн-школ. Если вы житель России, то на сайт можно попасть, если включить VPN. Если все же вы не знаете, что такое VPN, или не хотите его использовать в работе, то на сайт можно попасть через актуальную ссылку. Она находится по адресу supersliv.co. Итак, резюмируем. Жителям России обязательно включать VPN для доступа к supersliv.biz. А те, кто не умеет или не знает, что такое VPN, используйте актуальное зеркало supersliv.co. Заходите на сайт удобным для вас способом и получайте крутой контент ежедневно.
If people talk about AI, they talk mostly about LLMs. This means large language models. Think about ChatGPT. Yes, this is a picture that I have generated with ChatGPT. But for picture generation, we actually use most of the time a diffusion model. A diffusion model can make pictures, but it can also generate music, sound effects, voices, and even videos. And we can run all of this locally. So of course you can run diffusion models locally. Trust me, this will be easier than you think as soon as you get it. By the way, this is a complex workflow. And you can also run LLMs locally. This is a really simple interface with Ollama. So you can run LLMs and diffusion completely local. These are the two dominant forces in AI. Large language models and diffusion models. In the backbone of the large language model works the transformer architecture. The transformer architecture is simply the thing that was invented in 2017 that brought us all this cool AI stuff. On the diffusion models, actually diffusion works in the backbone. But now something cool. In the newest diffusion models also works the transformer architecture in the backbone, at least sometimes. If we come for example on Sora from OpenAI, this is a video generator, you can actually see that they used a diffusion model and actually combined it with the transformer architecture. Of course, they have also a whole technical paper. I don't want to go into detail in this paper. I just want to tell you that the diffusion and transformer is the technology that works nearly behind every single AI model. And in this video we talk firstly about the diffusion model, but remember also transformer can work in the backbone. I need to tell you how a diffusion model works, because as soon as you understand how these things are trained, you also understand later why prompt engineering is important. So let's just talk about the diffusion model, and in the next video we talk about large language models, and remember, the transformer architecture can even work in conjunction with diffusion. So this right here is a paper about diffusion models, and here we have a nice picture, and first I want to describe these pictures before we go on, because we need to get on the same page. So here you can see a picture of a dog, and here you see noise. First, we feed a computer a picture with a dog, for example, and we need to describe this picture to the computer with a detailed text. For example, a dog is sitting on the ground, a small shadow is casting on the ground, the dog is brown, the dog has black eyes, and so on. We describe it in detail. And then we go on and add a little bit of noise. And we do this over and over and over again, but still give the description to the computer. So we basically start with a picture and a description, and we add noise, and this process is called forward diffusion. Then we do it vice versa. We start with just the noise and give the computer text. And the computer starts to denoise a picture. So we start completely from noise and we give a text and the computer starts to denoise. So first we start to denoise a few pixels. And then the computer also take a look at the picture that he has seen previously, and he simply sees how good the computer does. And he do this backward diffusion again and again and again until we have the same picture back. So basically the computer tries to denoise a picture, always compares his results with the previous results, and in this process the computer learns to generate pictures out from noise. This is basically how this works. So forward diffusion, we add noise, then backward diffusion, we remove noise and simply look how good the computer is doing. If the computer is doing good, great. If the computer is not doing good, not so great. And we use the so-called reinforcement learning just like in any LLM. I have already explained the reinforcement learning a few times, so we will not go over this in more detail, but you can simply think of that we tell the computer, hey, you did a good job or you did not a good job. And then the neural net will get adjusted. This is basically how the computer learns. Now let's just take a look. Now I want to show you how this backward diffusion works. If we simply type in Super Mario and we send this out, right now we will do backward diffusion. We will start with just noise and then we will denoise a picture until we have Super Mario. And here in Midjourney we can see how the computer is doing the denoising process, so you can see now we have a clear picture of Super Mario. The computer did great, because the computer was trained for a long time with this. By the way, I use here Midjourney, so a closed source diffusion model as example, just because you can see the denoising so clearly inside of Midjourney. Later of course we will work with local AI, but Midjourney is here great for illustration. Now we need to take a closer look how this works in more detail. How the heck can a computer make a picture out of Super Mario? The first thing that the computer does is that the computer makes an embedding out of these words. Just like ChatGPT and every single LLM. These things work with token and they make first of all an embedding out of these words in order to understand the context. So let's dive a little bit deeper. We don't need to go that deep, but I want to explain you that the computer simply takes your words and then he will split it into tokens and so-called embeddings. So the computer don't understand cup of milk, the computer will translate this into computer language and the computer understands numbers. And a few of these numbers, a few of these so-called tokens can represent, for example, Super Mario or cup of milk. And then this so-called context-aware embeddings, this is the stuff that the computer can understand. So a few numbers are a context-aware embedding and then the computer can start drawing. But the computer is not really drawing. He simply manipulates pixels and I want to explain you also how this works in detail. So the computer makes your words into context-aware embeddings and he throws it into this right here, into the noise. And this first noise with the context-aware embedding is also called seed. So we start out with a picture that is entirely noise. And then we use our embeddings and we throw them to this noise. These embeddings, these are just numbers, for example 0.2 and 0.4 and so on. And this context-aware embedding could be, for example, Super Mario. And this context-aware embedding with this noise, this is now the seed. And this is the first starting point in order to make our picture. So basically we have these two things. We have noise and our context-aware embeddings. These two things are now called seed, like you know. And from this starting point on, the computer tries to denoise this picture. And he can do this because he has done it a lot of times and then with the reinforcement learning he got better and better. But now let's just take a look how the computer manipulates these pixels, how he can denoise this picture. So first this would be, for example, the seed. Just the noise with our context-aware embedding, and then we try to denoise this picture. And we do this over and over and over again, roughly 1,000 times until we get our final picture. And the important part is right here that we don't do this in one step, but we do this in 1,000 steps and the computer simply tries to manipulate a few pixels. So the computer does not draw, it manipulates pixels. Let's take a look how he does this. In order to understand the pixel manipulation, we need to understand what a picture is. A picture is just a grid. These are called grids with a few pixels. If we press on these, this is just a picture, this is a grid. This is a really simple grid and this is a grid with a picture with 18 times 18 pixels. So we simply have a few pixels and these pixels are all gray, and then the pixels start to change the color, and just with a few pixels we can also see that we get a picture that makes sense. This is a watermelon. So the diffusion model simply looks at every single pixel, what color every pixel needs to have. And the diffusion model understands this because he uses this context-aware embeddings, or especially like a few of these embeddings, and a few of these embeddings are called tensors, and with these tensors the diffusion model can simply see what color needs to be in what pixel. So the diffusion model understands what the context of these embeddings and tensors are, and then manipulates every single pixel, and it does this by manipulating the RGB color codes. Now let's just dive a little bit deeper. We can represent every single color with red, green and blue. And we can make also this into numbers, and you know that computers understand numbers. Here you can see, for example, that this color is, for example, red 255, green 204 and blue 204. And this green color is, for example, 204 red, 255 green and 204 blue. White is, for example, 255, 255, 255. And black is, for example, 0, 0, 0, and the computer understands this. So the computer understands the context of the tensor and of the embeddings, and he also understands the context of every single color because he understands these color codes, and then he goes on and manipulates every single pixel. An example of such a tensor that is translated into the RGB code would be something like this: 144, 145, 155. And if we take a look at these, 144, 145 and 145, and then we have our color. Here we have a perfect example that is a little bit easier because we have just black and white. It goes from 0 to 255, and here you can see that we can manipulate every single pixel, and then we can make a picture from this head or whatever this is. We can simply see that this is 157, 153, 174 and so on, and these are always different colors, and if we manipulate every single pixel we can draw pictures. So basically we can give every single pixel a color code, and the diffusion model simply does this. And of course the diffusion model understands every single color. So the diffusion model takes your word. It translates it into embeddings. A lot of these embeddings are so-called tensors, and in these tensors we have these color codes, and we manipulate every single pixel with such a color code. So we give every single pixel the right color, and we do this 1000 times in this so-called backward diffusion process, and then we get our picture. So basically the diffusion model looks at this noise and gives every single pixel a color code. Let's just say that this would be, for example, black. And black is of course 0. And the second pixel would be also black, for example 0. And the next pixel in this tensor would be, for example, 255. And 255, 255, so 3 times. And if we do this over and over and over again with every single pixel, sooner or later we can draw a picture. Just like you saw here, every single pixel gets a number, and then the diffusion model can paint. And this works with every single color because we have this color codes, this red, green, blue color code. So one last time, we start with noise. Then we give the noise our prompt. Our prompt gets of course translated into computer language in so-called tokens and embeddings, context-aware embeddings. A lot of them are called tensor, and with these tensor codes the diffusion model manipulates with the backward diffusion process with 1000 steps our picture until we have completely denoised our picture. And of course these diffusion models are trained on faces, on cars, on cities, basically on every single thing that you can think of. We train this diffusion model on everything. And so we can also type in, for example, here dog, cat, man, And the diffusion model starts to denoise every single picture. We can denoise dogs, we can denoise Super Mario, we can denoise cats, we can denoise humans, we can denoise every single thing that the diffusion model was trained on. And the important thing is that this context-aware embeddings, we can also play with these. If we type in cat, of course, we just look at the embeddings from cats. And if we give more context in this prompt, we can be more specific. We can type in, for example, an illustration of a colorful cat. And if we send this out, we will take a closer look at the context-aware embeddings of this thing right here, because we have trained on such a lot of data. We can denoise every single thing, and the diffusion model simply manipulates every single pixel and will give different colors as soon as we type in colorful. It will give different colors because we type in illustration. Every single thing just works with these color codes. The diffusion model can manipulate everything, as long as it is trained on these things. And this is how a diffusion model works. Computer is trained on a lot of pictures with text. We do the forward diffusion, then we do the backward diffusion and give the computer feedback if he is doing good or not. Then we do the reinforcement learning to tell the computer how he did, and as soon as the computer does good on a lot of different data, he can calculate new things. We can simply type in a word or a whole sentence. The sentence will get splitted in these tokens, in these embeddings, and then we will make a tensor out of this. These tensors with these color codes will simply manipulate every single pixel, and then we have our picture. This is how a diffusion model works. And of course, if we type in a cat, we get a random picture of a cat, and if we type in illustration of a colorful cat, we take a closer look at this context-aware embedding and manipulate the pixels so that we get what we want. This is how a diffusion model works. And in the next video we talk about LLMs, so that you also understand how an LLM is trained.
Привет! Данный курс скачан с сайта SuperSliv.biz. На сайт ежедневно добавляются топовые материалы от крутых авторов и лучших онлайн-школ. Если вы житель России, то на сайт можно попасть, если включить VPN. Если все же вы не знаете, что такое VPN, или не хотите его использовать в работе, то на сайт можно попасть через актуальную ссылку. Она находится по адресу SuperSliv.co. Итак, резюмируем. Жителям России обязательно включать VPN для доступа к SuperSliv.biz. А те, кто не умеет или не знает, что такое VPN, используйте актуальное зеркало SuperSliv.co. Заходите на сайт удобным для вас способом и получайте крутой контент ежедневно.